Picture this scene for a moment. A jumbo jet is descending through thick, rolling fog. Visibility is so low the pilots can't see past the nose of the aircraft. No runway lights, no horizon, nothing but gray outside the windshield. And yet, seconds later, the wheels touch down perfectly centered on the runway, smooth as any clear day landing. How is that even possible? The answer isn't luck, and it isn't a superhuman pilot with incredible eyesight. It's one of the most quietly impressive systems in modern aviation, and most passengers have no idea it even exists. To understand how this works, we need to go back to a time when fog simply meant flights got canceled. In the early decades of commercial aviation, if visibility dropped below a certain threshold, airports shut down. Airlines lost money, passengers got stranded, and there was no way around it. Pilots relied entirely on their eyes. If they couldn't see the runway, they couldn't land. That limitation became a serious problem as air travel expanded and schedules became tighter, so engineers began asking a difficult question. What if the aircraft itself could find the runway, without anyone needing to see it at all? The first real breakthrough came with something called the Instrument Landing System, or ILS. Introduced in the 1930s and refined over the following decades, ILS uses two radio beams broadcast from equipment near the runway. One beam, called the localizer, tells the aircraft whether it's lined up left or right of the runway centerline. The other, called the glide slope, tells it whether it's too high or too low on the correct descent path. Picture two invisible beams crossing in the sky, forming a narrow funnel that leads directly to the runway threshold. The cockpit instruments show the pilot exactly where that funnel is, even when the world outside is a wall of white. For decades, ILS meant pilots could descend safely through clouds and rejoin visual references at a much lower altitude, close enough to the ground to finally see the runway and land manually. But fog doesn't always cooperate. Sometimes visibility stays near zero all the way down. That's where the next leap in engineering had to happen, because a system that only gets you partway there isn't enough when the weather refuses to clear. This is where Autoland comes in, and it's a genuinely remarkable piece of technology. Autoland doesn't just guide the pilot, it flies the airplane itself from several hundred feet above the runway all the way to touchdown without a human hand on the controls. To make that possible, engineers had to solve a problem far harder than simply following a radio beam. The system needs enough redundancy that if something fails during the most critical seconds of flight, it can still land the aircraft safely. That's why Autoland-capable aircraft carry triple redundant systems. 3 autopilots, 3 sets of sensors, 3 independent computers, all cross-checking each other continuously. If one system disagrees with the other two, it's automatically outvoted and disconnected. This is called a fail operational design. The aircraft doesn't just fail safely, meaning it alerts the crew and hands back control. It fails operationally, meaning it keeps functioning correctly even after a component goes wrong, in an emergency where the runway can't be seen at all. That difference matters enormously. Airports need to be just as prepared as the aircraft. Not every runway supports these ultra-low visibility landings. Airports rate their approach capability using categories, commonly known as CATT-1, AT2, and CAT-3. CAT I allows descent down to around 200 feet with a certain minimum visibility. CAT-2 lowers that further. CAT-3, the most advanced category, is split into subcategories, with CAT-30 theoretically allowing a landing with zero visibility whatsoever, no decision height at all. Very few airports certify to that extreme level, but many major international hubs support CAT-3, allowing landings when visibility is reduced to just a few dozen meters. Airports like London Heathrow, Paris Charles de Gaulle, and several hubs in the Pacific Northwest see this kind of fog often enough that CAT-3 operations are practically routine rather than exceptional. Airlines flying into these airports train specifically for them, and dispatchers watch weather forecasts closely, because a runway certified for CAT-3B one day can lose that certification temporarily if a piece of ground equipment goes offline or a light fails an inspection. Achieving this isn't only about the equipment in the cockpit. The runway itself becomes part of the system. Extremely precise lighting is embedded into the pavement, calibrated so the localizer and glide slope signals remain accurate to within inches. Sensitive areas around the antennas have to be kept completely clear, because even a vehicle or another aircraft sitting in the wrong spot can distort the radio signals enough to throw off the approach. That's why during heavy fog operations, ground movement at the airport often slows down dramatically. Everything becomes about protecting those invisible beams. Inside the cockpit, the crew's job during an Autoland shifts significantly. Instead of manually flying, pilots become monitors, watching the automation with extreme focus, ready to intervene if anything looks wrong. Before the approach even begins, they run through detailed checklists confirming the aircraft The airport and the weather all meet the strict requirements for that category of landing. If any single element falls short, the automatic landing simply isn't permitted, and the crew has to divert to another airport with better conditions or wait for visibility to improve. Once cleared, the aircraft intercepts the localizer and glide slope, exactly like a normal ILS approach, but now the autopilot is doing all of the flying with far greater precision than a human ever could in these conditions. As the aircraft nears the runway, radio altimeters measure the exact height above the ground, and the system begins a carefully choreographed flare, gently raising the nose in the final moments to soften the touchdown, all without a single human input on the controls. After touchdown, the autopilot can even keep the aircraft tracking straight down the center line during rollout, using the same localizer signal, until the crew takes over to taxi. It sounds almost too smooth to be real, and in a way, that's the point. This entire system exists so that a landing in zero visibility feels exactly as uneventful as one on a clear sunny day. Passengers in the back rarely realize anything unusual happened at all. They just feel the wheels touch down and assume it was a normal arrival. Of course, none of this happens without extensive testing and certification. Before an airline is approved to perform Autoland in low visibility, its aircraft, its training programs, and its maintenance procedures all go through rigorous scrutiny. Pilots practice these approaches repeatedly in simulators, rehearsing not just the successful landing, but every possible failure scenario, engine problems, sensor disagreements, missed approaches triggered at the last possible second. The goal is to make sure that no matter what happens, the crew has a clear, practice response ready. There's also a common misconception worth clearing up. Autoland isn't reserved only for genuine emergencies or fog-choked runways. Many airlines require their pilots to perform a certain number of autolands even in perfectly clear weather, simply to keep the system exercised and the crew current on the procedure. So if you've ever felt an unusually gentle, almost too perfect touchdown on a clear day, there's a real chance the computer was flying that landing, not the pilot. What's most remarkable about all of this isn't just the technology itself. It's the layers of redundancy stacked on top of each other, the radio beams, the triple computers, the precisely calibrated runway lighting, the strict categorization of airports, and the extensively trained crews who know exactly when to trust the automation and when to take back control. Every piece exists because engineers refuse to accept that fog should simply ground an entire industry. So the next time your flight descends into thick, gray nothingness and you can't see a single light outside your window, remember that somewhere in that cockpit, an extraordinarily precise, triple redundant system is quietly guiding hundreds of tons of metal to a landing more accurate than most pilots could achieve by sight alone. It isn't magic. It's just decades of engineering, built to solve one simple, stubborn problem. What happens when the runway simply refuses to be seen? And that raises another question worth exploring. If computers can land an airplane this precisely, why do we still need human pilots in the cockpit at all? I've got a video covering exactly that question on the channel,